Right, good morning, everyone. Questions, as usual, you guys can put them on chat. In the meantime, I will just remind you the strategy for evaluating trigonometric integral. Okay. So what we saw yesterday was the following trigonometric integral. So integral of this form. Mx dx, this type of integral. And the way we do it is we actually consider two cases, clear-cut cases, very clear-cut. Case one, if n or m odd. Another way to say, if at least one of them is odd, at least one power is odd, then the idea is to split the odd power and set u to be either sine or cosine, or u equal to cosine. So that was our strategy, and use the identity sine square plus cosine square equal to 1. So if at least one of them is odd, or if both are odd. Okay, now if n and m even, and the end is important, if both are even, use the half angle formula. Okay, and do not mix the both approach. So if at least one of them is odd, this is the approach. If both are even, we use the half angle formula. We do not mix and match both approach. All right, so let's look at what questions you guys have. So we look at 23. And 23. Okay. So that's the integral of sine square cosine square dx. Okay. So this is even and this is even. Both are even. Then we use the half angle formula for each one of them. So let us see is equal to 1. This will 1 plus cosine 2x divided by 2 times, sorry, that's a minus, 1 minus cosine 2x divided by 2 dx. Now we just multiply out, no, that's the plus. We multiply them out and we proceed. A half times a half, that's 1/4. So I can take 1/4 out. Times 1 minus cosine 2x times 1 plus cosine 2x. And that's what leaves me, was 1/4 times. Now I multiply this by this. Just multiply them, distribute. So I will get 1 minus cosine square 2x dx. Okay, and now what should I do at this stage? What do you want me to do?
Wouldn't we have to do it again?
We have to do it again. That's cosine square 2x. We have to apply the half angle formula again, because the advantage of the half angle formula is it gets rid of the power. And that's really what's really giving us problem in this case. And it gets rid if it's an even power. Not really odd, is problematic. So it's gonna give me 1/4 integral of 1 minus 1 a plus, because I have 2x, it's gonna turn into 4x over 2 dx. Now I'm going to do what I did yesterday. 1 minus, I'm going to distribute that. So I can, that's a numerator, it could be split, it's not a denominator, I can split a numerator, and this is going to give me minus a half, minus plus minus cosine 4x divided by 2 dx. And we're almost done. This will give me 1 minus a half, that's a half, minus a half cosine for x. And now it's time to evaluate each term. 1/2 antiderivative, sorry, my apology. 1/4 antiderivative of 1/2 is a half times x minus a half. Antiderivative of cosine for x, because I have to use substitution here, and this would give me 1/4 sine for x plus a constant c. So finally, I will get 1/8x minus 8 times 4 Okay, questions before we move on? Okay, so before we move on to the other question, one of the integral that is coming up a lot with us and will always come up is integral of the form cosine kx dx, where k is a constant. Okay, so this integral is always equal 1/k sine kx. Okay, how do we go from here to here? Why is this true? If I tell you, show that this is true, what would you do? Okay. If I tell you, convince me that, show that this is equal to that, how would you do it?
You could just derive the right side.
That's one way. What's the other way? You're absolutely correct. What's the other way?
Why don't we just start by u substitution?
Exactly. Another way is to do the u substitution. Okay, so either you differentiate the right side, you get the inside, absolutely, or because you will have, most of the time, you guys will have to compute this, most of the time as realized, then it's you do u substitution, u equal kx, and then you get that. But because we're going to use those integral a lot, you can go ahead and use the formula without having to do substitution every time. Okay, because simply you're going to, as you realize, they are coming up almost all the time now. So let's look at number 64. Okay. So what's 64 about? 64. Find the volume of the solid generated when the region bounded. So we have the region bounded by y equals sine x. And the x-axis on the interval 0 pi. So that's my region, sine x. So this is the sine. And this is pi. And we are rotating it around the y-axis. Okay, so we're going to rotate this around the y-axis. And they want us to find the volume. So we get like, the book is calling it sine football, because when you rotate this region, you're basically going to get like a football, like this oval. All right, so we're going to use the shell method, sorry, the washer method. So we're going to take typical slice, that's my xi. I rotate it. It's going to generate a cylinder. We're going to find the volume of a typical cylinder and then evaluate. So first, volume of a typical cylinder. Because we're touching the x-axis, so we're going to get a cylinder, or the disk if you want. It's going to be equal pi times the radius squared times the delta x. This is my delta x. And from here to here, that's my radius. If this is xi, my radius is divided sine xi square. Okay, so that one of typical this. So the total volume is going to be the integral from 0 to pi of pi sine square x dx. So now we are in a universe that we understand very well. There should be no problem integrating. So this is equal to pi times sine square, the power is even. We use the half angle formula, 1 minus the cosine 2x over 2 dx. 2 is a constant, I can take it out. Pi over 2, the integral of 1 minus the cosine 2x dx. So finally, this is equal pi over 2 times. And the derivative of 1 is x. Cosine 2x, my k is 2. So it's a half sine 2x evaluated between 0 and pi. Okay, so it's one of those basic problems we did at the beginning. So now finally I will get pi over 2 times. The upper limit is going to give me pi minus a half sine 2 pi minus at the lower limit. It is 0 minus a half of 0. So finally, we end up with pi over 2 times pi sine 2 pi is 0, 0, 0. So we get pi square over 2. Okay.
Professor,
Yes.
if we used substitution, would we get the same answer?
Substitution where?
For sine x, made u equal to sine x.
Let me make sure I'm following. At which stage? Here?
The very first, yes.
No. Watch what happened. Watch what happened. Why do you want to use the substitution? Let me follow your logic. Okay, what substitution you want to make?
Let's make u equal to sine x.
What's the du?
Cosine x.
Okay. How do you want me to do here? Everything has to be in terms of u. What do you want me to do?
So it would be the antiderivative of u squared
Okay.
du.
No. No.
Oh,
No. Why no?
okay.
Why no?
Because it's just dx. We
Right.
have to,
You don't have cosine x at all in the picture.
right, right.
Totally collapses.
Okay.
Substitution has to be clear. Very good. So let me look at 67, and then we're going to proceed to another type of trigonometric. So let's what's 67 about. Okay, those integrals will come up with you a lot. So, but you just have to use a formula to do them. I mean, without the formula given to you, there is no way we can do those. So it's sine 3x and cosine 7x. So it's not really the same inside here. So those problems, they are not hard to evaluate. It's just a formula. So the formula we're going to use is the following. So the formula is given to you in the book. And it tells me that if you have sine mx, so that's one of those trick formula that you will never memorize, but we should know that they exist, is equal to, no, sorry, I don't need this one. Sine mx cosine nx is equal to a half sine of the difference plus sine of the sum. And that's the only way we can evaluate those type of integral. Okay, so let's do that. This is going to become equal to the following integral. So instead of this term, I'm going to substitute it by that. So there's a half times sine of the sum, which is 10x. Sorry, the difference, it doesn't really matter. It's m minus n, 3 minus 7, plus sine of
Shouldn't
the
it be -4?
Of course. Thank you. Plus the sine of the sum, m plus n 10x. Okay, so that's the only way really to evaluate this integral, because I mean, we have the inside here is really changing. So we don't really have any substitution, any logical substitution to do, because you put u to be the sine 3x, the derivative is 3 cosine 3x, but you have a 7x in here. So those substitution will totally fall apart. And the only way to do them is to use those trig identity. Now this is equal to, and now each one by itself. So it's a half the integral of sine of minus 4x plus the sine of 10x equal to a half times. Now I'm finding the antiderivative of each. This is again of the form sine kx, where k is a constant, and my k here is the -4. So it's going to be equal to 1 over -4 times, because it's a sine, its antiderivative is going to be minus the cosine, plus antiderivative of that, the k is 10. It's 1 over 10. Because it's a sine, the antiderivative is going to be minus the cosine. And now we clean it up a little bit. I will have a half times. Minus minus is a plus, 1 over 4. Cosine for x x plus c. Questions before we move on? Okay, you guys quiet. Okay. I used the property of the cosine here. Which property of the cosine I used? Usually you guys complain when I do something that you don't follow.
Was it the equation that was given to us? The sine mx. Oh.
No. I use the property of cosine. Why did the minus disappear? I didn't forget it this time. I had minus for x, now I have 4x. Do I have the right to do that? Anybody? Anybody remember that trig property? Okay. One of the property of the trigger of cosine is cosine minus t is the same as the cosine of t. Okay, so the cosine of minus t is the same as the cosine of t, because on the unit circle, if you guys remember your unit circle, if this is t, the cosine is the x coordinate. Minus t, right here, the cosine is the x coordinate. So they're absolutely equal to each other. So instead of minus 4x, I can just keep it cosine 4x, because those are absolutely equal to one another. That's a small comment to remind you some of the property of trig function.
But like, if we put -4, it would be correct. That would count correct as the answer, right?
Yes, but it's nice to know those stuff. It's nice to know it, especially at this stage of your learning. Okay.
Does that also apply to sine?
What do you think is the property for the sine? Use the unit circle, if you guys remember it. The sine is the y coordinate.
Is it equal to the negative sine of t?
Right, exactly. The sine is the minus, is the y coordinate. So the relationship between them is it's minus the sine of t. Okay, so those are nice property that you will definitely use in your in physics and everywhere. All right. Okay, so what we're going to do today? Today we're going to take trigonometric, also integral, that involves secant and tangent. Okay, and those I usually wave my hand a little bit. I don't do them as thoroughly as the sine and cosine because they get messy. So, but I will do enough. So integral of the 4. So still with the same section, we're not changing. Secant nx, tangent mx dx, this type of integral. Okay, so before we even step into them, you know, sine and cosine we kind of know. Secant and tangent we tend to forget a lot. So let me remind you the basic of them. First, let us remember the derivative of tangent. Anybody remember? Because to work with integral antiderivative, I have to know my derivatives well. So anybody remember what's the derivative of tangent?
Is it secant squared?
Here you are. It's secant squared. So it means that the antiderivative, that's important, of secant square, looks like a nightmare, is actually tangent. Okay, first property. Second, what's the derivative of secant? Anybody again remember that?
Is it secant tangent?
Here you are. Secant tangent, absolutely correct. Secant tangent, okay? Something else also we will need to use. We have to find the property of those. Now, there is still one properties. In the previous problem, when we took integral involving sine and cosine, we needed the trigonometric identity that to be able to do the substitution that related the sine and cosine. And the trig identity was sine square plus cosine square equal to 1. Okay. Now, what's the trig identity that relate the secant and the tangent? So there is another identity that relates secant and tangent that we're going to use a lot. Anybody remember it? Maybe not. Okay. If I start here and I divide across, so divide across by cosine square. Okay, divide across by cosine square. What do I get? If I divide this by cosine square, divide this by cosine square, and divide this by cosine square, what does this give us? So I divided across, which is mathematically is the correct thing to do. What this will give me? The first one will give me what?
Tangent squared.
Plus
1
equal
secant squared.
secant square. That's the trig identity that relates secant and tangent. And that's the one we will be using because we're going to use almost the same strategy as we use for sine nx, cosine mx. We're going to use very similar strategy, but so we need this relationship that exists between this tangent and secant. So now I write it here. So to put all of them together, so secant square, is 1 plus tangent square, or you can write it as secant square of x minus 1 is tangent square. Okay, so those are the relationship between the tangent and the secant. Those are the basic relationship. Okay, and now with that, I'm going to put up some problems. As I said, I will not put all the rules because there are so many. I will put some rule, or I'll make them so that you guys can figure them out. We're going to use almost the same strategy as we did for sine and cosine, splitting stuff. But you have to tell me how you're going to split them. Okay. So I'll start with my first problem. And an easy one. Suppose I give you the following integral. Evaluate. Integral of, what do I want? Tangent for x, secant square x dx. Right? I want you to see connection and then tell me how to do it.
Should we split the tangent?
Yeah, why?
So that we can substitute for tangent squared?
Okay, so I'm gonna take scratch piece of paper where I put all your ideas, and then we do here the right stuff. So you want me to separate the tangent. So you want me to write it as tangent squared times tangent squared?
Yes, sure.
Okay, whatever. All right. And then what's the benefit?
Then can we substitute secant squared? No, because there's a 1. So it would have to be secant squared minus 1.
Each one of them?
Should we do it for both of them?
I don't know. I'm just doing exactly what you tell me. Look more carefully, all of you. Look very, very carefully.
Couldn't we use substitution where u is the tangent of x?
What's the benefit?
Because then the secant squared of x would be du.
Absolutely correct. All right. So the reason I started where I start is if you guys are writing, keep those in front of you the whole lecture. All right. Keep them. You know, stare at them. Okay, the derivative of tangent is secant squared. So the way we're going to do that is, all right, this could be written as. So the way your classmate tried to do it wasn't really getting us anywhere in this problem. Now, if we look carefully, the derivative of the inside, the derivative of tangent is secant square x. Right there. So we're gonna do it, substitution. We're gonna put u to be tangent. Du is the secant square x dx. And that would be the integral of u to the power 4, and this would be the du. Okay, so the secant square x dx, the secant square tells us that, you know, that's the derivative of tangent. So now can I work with that? And indeed we can. So this will give us 1 over 5 u to the power 5 plus c. It means 1 over 5 tangent x to the power 5 plus c, end of the problem. Now, of course, differentiate this, you're definitely going to get that. All right, so having the secant square is actually what's helping us put u to be tangent because that's the derivative of tangent. I'm going to play on this a little bit. Let us say I have let me start a new piece of paper here. So suppose I give you the integral of, I'm not gonna change the power of tangent, but I'm gonna change the power of secant. Okay, and let's see how we're gonna do that. And I said we're gonna imitate a little bit what we did for sine and cosine. Okay, I want you to kind of little bit look at it and see what we can do. Anybody with any idea, you know, kind of let me know.
split secant to the fourth into secant squared and secant squared, and then one of the secant squareds make tangent squared plus 1.
Okay, what's your end goal? So she wants me to split this into okay. And what do you want me to do after that?
Make one of the secant squareds tangent squared plus 1.
Okay, make one of them tangent squared plus 1. And what's your end goal?
Let u equal tangent, and then
Absolutely.
use an equal secant squared, and then you can substitute.
Exactly. So what she said, okay, you have secant 4 dx, split it into secant square and secant square. Now, secant square, that's really where the identity come into the picture. Secant square can be substituted fairly easily in terms of tangent square. This is 1 plus tangent square. It's a very easy substitution. And then the other secant square, it could be used for the u equal tangent. So here we're going to set u to be the tangent of x, and my du equal the secant square of x dx. And now everything will be in terms of u in an easy way. That's u to the power 4, u squared plus 1. And this term now gets swallowed up by the du. Okay. And this is going to be equal to. Now that's easy. u6 plus u4 du. 1 over 7. u to the power 7 plus 1 over 5 u to the power 5 plus c, giving me 1 over 7 tangent x to the power 7 plus 1 over 5 tangent x to the power 5 plus c. Okay, so the idea here, secant 4, we want to bring up, split off the secant square, and the benefit of splitting the secant square is that I can put u to be tangent, and I can substitute everything in terms of tangent. So before I give you the first rule, I'm going to give you a problem and see what you guys have, come up with. So suppose I give you the following. Okay. Integral of suppose I give you integral of tangent cube x secant cube x dx, something like that. Okay, and I want you to interact a little bit with it and tell me what to do. So my goal is to give you a rule here, but I have to tell you why the rule work here. So give it your best shot, this problem.
Are you gonna have to split?
I want you to decide. I want you to decide. That's the goal.
Hold on.
Okay? I want you to decide. So I want you to work it for a few minutes in front of yourself, and then I'll take it by myself.
Split secant cubed to secant squared and secant x.
Okay.
So then once tangent becomes u, you can take the secant squared out.
Give me 1 minute. I'm not that fast. Okay, so you want me to split this as imitation to what we did before, right?
Yeah.
So it's going to be split into secant x, secant squared x dx. With me?
Yeah.
Okay.
Then make u tangent.
U equal tangent. The du is
Secant squared.
dx. And then this is going to give me. Okay, what this would give me? All of you pitch in so you understand, why we're doing the splitting, and how should we do it? All right, what do you want me to do now? Keep going.
So you'd get u cubed secant x du.
Can we keep secant x? When we do substitution, what are we supposed to do?
You're supposed to get it all in terms of tangent.
Very good.
So that doesn't work
Because
because
what's
secant.
secant? X in terms of tangent. It's not it doesn't work. It's hard. Because secant square is 1 plus tangent square. So secant is the square root. So it's going to give me the square root of 1 plus u squared. Is this an easy integral to proceed? So I'm going to have u to the power 3 times square root of 1 plus u squared. Watch carefully. Substitution would not work naturally because the derivative of that is a u, and I have u to the power 3. So when I'm splitting, I can split the secant square, but the part that I'll be left with is the secant. The secant is problematic because it's the square root of 1 plus u squared, which is hard to integrate because now I have u cubed, the square root. So it's not really improving a whole lot. So when do you think is a good idea to split into secant square and another term? What should be the condition? What is it I would like to have here? What caused me the problem here?
Maybe when it's even, you split it.
Right, when it is even. Because if it's even, then I don't have the square root term to really play with. That's really the benefit of having to be even. So if the power of secant is even, then you split and into a secant square and something else. If the power is odd, you're going to encounter this problem because it's going to come up with the square root. Okay, so the first rule, if you want to memorize it, it's up to you, or you want to understand it. So the first rule, one of the rule is if the power of secant is, if the power of secant is even, then split the secant so that a secant squared term remain. And set u to be tangent. Okay, so if the power of secant is even, then you can split the secant so that this term remain, and then you'll have something else, and then set put u equal tangent. So split off the secant square term, but the secant has to be even, otherwise it's problematic. So we took care of even power of secant. And now I'm going to go back to the other problem and see how we're going to solve it. Okay. So I'm going to take up this problem and see how can I solve it. So u equal secant was problematic. U equal tangent was problematic. So how are we going to solve that?
Break up the tangent into tangent squared and tangent, and the secant into secant squared and secant, and then let u equal secant.
Right. So the way we're going to do it is like that. So here, that's how we're going to be the approach. And then we're going to come up with a rule. When do we do that? Times a secant cube x dx. Breaking secant square, I hope I convinced you somehow that it's not going to work. So the way we are going to do is we're going to try to split off. That's what the idea, to split off a secant tangent term. And then we're going to set u equal secant x. That's really going to be the technique. We're going to split off a secant tangent term and then put u equal to secant. So how we're going to split off the secant tangent? We're going to get a secant from here, and we're going to get a tangent from here. And this would work. You will see in a second the benefit of that. So this is going to be equal to, I'm going to split that into tangent square times tangent. Split that into secant square times secant. And finally, not finally, I will end up with tangent square, secant square, tangent, secant dx. So I'm going to split off this term. The benefit of is that this term, when I split it off, that's the derivative of secant. So that's the derivative of secant. And that's really what's going to make it kind of workable for us. So now I'm going to put u to be secant. The du is secant tangent dx. Now everything has to be in terms of the u. And am I safe in this case? Am I safe? Secant square could be put easily in terms of u. Tangent square. So I need this even power now. Could this be made easily in terms of secant?
Yes.
Yes.
Absolutely. So this is secant square minus 1. Easily. And then finally, I will have u square. So I need that. I need this power here times u square du. Okay, so as I said, I hate the section particularly, sine and tangent secant. I don't like it because there are so many rules. So I'm trying to make it as intuitive as possible. So that's u to the power 4 minus u square du. Okay. And now it's just the regular stuff. So it's 1 over 5, u to the power 5 minus 1 over 3, u to the power 3 plus c. It means 1 over 5 secant x to the power 5 minus 1 over 3 secant x to the power 3 plus a constant c. Okay, so let us sum up and then ask ourselves under what condition can we split a secant and tangent and put u equals secant? What going to be the issue? So I put the problem in front of you, and my question is, what will make what will make the substitution hard? What can get into the picture? Before I set up the rule. Which condition will make this substitution problematic?
If the tangent isn't also odd.
If the tangent is what?
If they're not both odd at the powers.
Which one is problematic actually? Let us say, if you guys are done writing, let us say this is 4. Do you think the approach would work? We have another approach to deal with it when it is 4, but do you think it will work? All of you.
If u is secant x, then I guess it would work.
Yeah, because this will become what? Secant cube.
Yeah, but then it would just be u cubed. So
yeah, so there is no problem. So having a secant with even power in this case is really not an issue. Which one do you think is going to be the issue?
if tangent was
Tangent will be the issue. If I have tangent 4 here, then if I break it into this cube, then I'm going to have problem here. Tangent cube is not going to be secant square. It's going to be this to the power 3/2. And I'm going to have a mess in my hand. Okay, so it's really the power of tangent. So if the power of tangent is odd, then I am safe. I can split off the secant tangent term. So the second rule would be, if the power of tangent, And believe me, if you guys can understand those, you don't have to memorize all this stuff. So if the power of tangent is odd, split off if possible, because sometimes it's not going to be possible. Split off if possible. It means you need a secant in the picture, a secant tangent term. And set u equal secant. Okay. So now I took two cases, which are clear-cut. The third case is a mess. And then in the third case, I will tell you, just use your creativity. So let me sum up the two cases that we have. So this integral, secant mm dx. So m even, it means the power of secant even, actually, power of secant even, split off the secant square term. Split off secant square and set u to be tangent. Okay. Now, if the power of tangent odd, then split off a secant tangent term and set u to be secant x. What's the last case that we may encounter?
If the power of tangent's even and the power of secant's odd.
Yeah, power of tangent even. And this is where I really don't have rules. So I give you ideas here, ideas. Try u equal secant. Try u equal tangent. Try stuff. Use creativity. And I know you're not gonna like that. And the last thing, sometimes what helps, write everything in terms of sine and cosine. Sometimes this also can be very helpful. Write everything in terms of sine and cosine. And use what we've learned about sine and cosine. So in the last case, when the power is tangent, when the power of tangent is even, then start trying stuff. I mean, try secant, try tangent, use the identity secant square equal 1 plus tangent. Try anything that comes to your mind. Or in the worst case scenario, sometimes writing everything in terms of sine and cosine will do for us. So it's just really a matter of trying here. So in the two cases that are clear, this one, it becomes problematic. And as you guys know, in the worst case scenario, go use an algebra system and figure it out. I don't really care that much about that scenario. All right, so I would like to do now two more integral. I think they are important and we should know them. That has to deal with tangent and secant that don't fit exactly into those scenarios. So I will do two simple ones, they are fairly simple, but I would like you to, we should know them. So some simple integrals. My apology. So some integrals. Okay, the first integral I want, which is the basic one. How to compute the antiderivative of tangent.
Would you put it of sine over cosine and then do u substitution?
Right. Sine over cosine. There is no way out. Sometimes, as I said, if there is no secant in the picture, there is really nothing really to work with. So absolutely, we're going to put u to be the sine of x, cosine, du is minus sine, and that's an integral that we definitely have to know. It's going to be equal to sine x dx, that's minus du. So minus du. So this is minus 1 over u du. It means minus ln of u. It means minus ln of cosine x. Okay, so antiderivative of tangent, none of those what we've learned actually work because all of them involve tangent and secant. There is nothing here. That's how we do it. Okay, one more integral that we have to know. Some of the basic one. Tangent square. Okay, this is the scenario where the power of tangent, I don't know. What do you want me to do? The power of tangent is even. So this is one of the bad scenarios, but this is an easy one. Can anybody come up with any idea? So we can go.
Could we just do what we did last time?
What?
Cosine.
It's sine square over cosine square.
Can you change it to the secant squared x minus 1?
That's the best way. I'm going to rewrite it as, try to do it sine square of cosine squared. You're going to have definitely problems because when you have sine square, you have to use the half angle formula. You have sine square over cosine square. It's not going to work. So this is the easiest way is actually rewrite it as secant square x minus 1. Okay, so we use everything. When you hit those, you have to use, as I said, creativities, the trig formula we've learned, anything, and see which one will help. Now, why is this helpful? Why is this helpful?
Because you can make secant x u, and then the du becomes secant x tangent x.
Ooh.
Can you just take the antiderivative right then and there? Because secant square would be tangent. And then
Right. That's why this is easy. And this is will point out, remind you something. What's the antiderivative of secant square?
tangent.
I know that tangent. I know that we forget this. I know that, but I'm reminding you so you don't. Antiderivative of secant square is tangent. Okay, I'm putting it in front of you to remind you. So the antiderivative of that is going to be tangent. Antiderivative of 1, it's x plus c. Okay, so that's why I told you when the power here is even, creativity is the key. There is no magic. You have to think about what will work in this particular problem. Okay, and we're starting to use this, so start to kind of, internalize it a little bit. All right. The class is done. Your homework is on Brights, on whatever, on MATLAB as usual. And if anybody has question, can stay. Anybody else?